previous video, we studied sign conventions that are used for the variables in the mirror equation. In this video, we will solve the examples based on this equation. We will see examples on concave mirrors first. Here is a question put on your screen. Go through it carefully. Okay, so let's note down given things first. We are given focal length of a concave mirror as 5 centimeters. Well, for this problem, there's no need to draw a figure, but we will do it here anyways. So f is equal to 5 centimeters, right? Be careful. Don't forget the sign conventions. The third rule says that the distances parallel to the axis and to the right of the mirror are taken as positive, and the distances to the left of the mirror are taken as negative. So f will be negative 5 centimeters. What else are we given? We are given object distance u as 8 centimeters. Again, using the sign convention, this will be negative 8 centimeters. We want to find the position of the image from the mirror, that is, we want to find the distance of the image from the mirror. By just looking at the position of the object, can you tell me where will the image be formed? Pause the video and give it a thought. Well, we know that the principal focus F is the midpoint of segment CP. C is the center of curvature and P is the pole of the mirror. So if the principal focus is 5 centimeters away from the mirror, then C will be 10 centimeters away from the mirror. So our object is between C and F, and we know that in this case, its image is formed somewhere behind C. Also, this is a real and inverted image, and on the left side of the mirror. So the value of image distance from the mirror should be negative. Let's find out if that's true. We will use the mirror formula to find the value of image distance V. So we substitute values of f and u in the formula and solve it. And finally we will get V as negative 13.333 centimeters. So indeed, we got the negative value, justifying that the image is formed to the left. And as the value is more than 10, we can be sure that it's formed behind point C. Shall we try out another one? Okay, here we go. Again, go through it carefully. The given object here is a light bulb, and its distance from the mirror is 8.1 centimeters. The focal length is 14.2 centimeters. We're also given something else. And what's that? We are given the height of the object, which is the light bulb, as 4 centimeters. We don't really need this height here. This is just given to confuse you. We are asked the value of V. Again, we will use the mirror formula to find it. Tell us your answers in the comments section below. These were a few problems based on concave mirrors. In the next video, we will look at a couple of examples based on convex mirrors. In this video, we will look at a couple of examples based on the mirror equation. This time for convex mirrors. Are you ready? Okay, I have put 2 questions on your screen. Pause the video and try to solve them yourself. Let's start with the first question. We are given the object distance from the mirror as 20 centimeters. And we know that the value of u is always negative. We are also given the radius of the curvature of the convex mirror as 30 centimeters. What is the radius of the curvature? We know that it's the radius of a sphere of which the reflecting surface of a mirror forms a part of. So from this sphere, we see CP is also the radius. So the length of CP is 30 centimeters. We need to find V, and for that, we need to find the value of F first. This F is nothing but length of FP. So how do we get the value of F? We know that F is a midpoint of CP. It means that if CP is 30 centimeters, then FP will be 30 over 2 or 15 centimeters. And what will be its sign? Yes, In a convex mirror, the principal focus lies to the right of the mirror, so its value will be positive. Now we will substitute values of U and F in the mirror formula and solve it further. So the image distance that we get is about 8.57 centimeters. So this distance is 8.57 centimeters. As it's positive, we can say that the image is formed on the right. This was about the position of the image. Is this it? Are we asked for anything else? Yes, we are also asked for the nature of the image. Is the image formed real or virtual? Well, by now, we know that the image formed by a convex mirror is always a virtual image. No matter where the object is kept in front of the convex mirror, the image formed will always be a virtual image. So that completes our first question. Here's the second one. I will leave the second problem for you to solve. Tell us your answers in the comment section below. There are various properties of images formed by spherical mirrors: the position, the size, and the nature of the image. These properties vary as the object's distance from the mirror varies. The property that we are going to discuss in detail in this video is the size of the image. For a concave mirror, there are three possibilities for the size of the image relative to the object. Basically, the image can be enlarged, the image can be of the same size, or also can be diminished or smaller in size. For a convex mirror, the image is always smaller in size unless the object touches the mirror. In that case, the image will be of the same size as the object. Now, if we were to compare the size of the image with the size of the object, then we will take their ratios. That is, the ratio of size of the image to the size of the object. And this ratio is what we call magnification. It's denoted by the letter M. Let's move to a new page. In our ray diagram, the sizes of the object and the image are nothing but the heights of the object and the image. So M will be equal to HI over HO. Let's do a bit of math now. Suppose the height of the image is greater than the height of the object. This means that the image is enlarged. Now answer this question. If the term in the numerator is greater than the term in the denominator, then the ratio will be? Yes, their ratio will be greater than 1. What if HI is less than HO? Yes, the ratio will be less than 1. The image is diminished. What if they're equal? Their equality implies that both the object and the image are of the same size. The ratio will be 1. If you notice that in all three cases, we are assuming something. We are assuming both HO and HI to be non-zero. But can they be zero? We know that when the object is at infinity, its point-sized image is formed at the focal point. So here we can take size of the image as 0. However, theoretically, we say that when the object is at infinity, the image is point-sized. But in reality, this is not a point-sized image because we cannot define infinity. The image, however small it is, still has some dimensions. So in reality, HI cannot be 0. It can be a really small number, for example 0.00005, but never 0. We can apply the same logic for the object size. So HI and HO cannot be 0 in reality. Now there is a relation between the magnification and the object distance U and the image distance V. The relation is that HI over HO is equal to negative V over U. This relation is very easy to prove. I will give you a rough sketch of its proof in another video in this playlist, but first let's solve a few problems based on magnification. Here's the first problem. We will see the solution in the next part of the video. Problem I left you with in the previous video. Before moving on to the solution, let me bring you to some sign conventions that we had seen in our previous videos. Here they are. Yes, these sign conventions also apply here. For instance, if the image formed is above the principal axis, then HI is taken as positive. And if the image is a real image formed below the principal axis, then HI is taken as negative. Let's come back to our question. Go through it carefully. Here we are given a convex mirror as a side view mirror of an automobile. The radius of curvature is 3 meters. Since this is a convex mirror, this value will be positive. Well, we know that the focal length is half the radius of the curvature. So f will be equal to 1.5 meters. We are also given object distance from the mirror to be 5 meters. Since the object lies on the left-hand side, u is always negative. We need to find 3 things: position of the image, the nature of the image, and the ratio of the image and the object size. Well, this ratio is nothing but magnification m. To find the position of the image v, we will use the mirror formula. On solving further, we get the value of v as positive 1.15 meters. And since this is a positive value, the virtual image is formed behind the mirror. What about the ratio? We will use the formula m is equal to negative v over u. Substituting the values of u and v and solving it further will give us m as 0.23. What does this tell us? Since m is less than 1, it tells us that the image size is lesser than the object. So the image is virtual and diminished. That's the nature of the image. Now here's one more question on your screen which I will leave for you to solve. Don't forget to share your answers in the comment section below.